Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in. Adjust your pillow, let your body sink a little deeper. There's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the evening has finally stilled? A cosy space where the day's noise has faded into silence? Wherever you are, you're welcome here. Tonight, we're going to explore something quite remarkable. In late 2023, astronomers noticed something peculiar about an object that had visited us years earlier. An interstellar wanderer named 3I/ATLAS had passed through our solar system, and we thought it had left. But then we discovered something unexpected. We'll explore what made this realization so fascinating, understand why it took us years to notice, and contemplate what it means when visitors from beyond our solar neighbourhood leave traces behind. But don't worry, this isn't going to be a tale of cosmic danger or alarming discoveries. Instead, we'll move slowly and carefully through the observations, the detective work, and the beautiful science that revealed this unexpected story. By the end, I think you'll find that surprises in astronomy are often invitations to deeper understanding, not causes for concern. If you enjoy these calm explorations of space and mystery, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this quiet community of wanderers. So settle in, let your shoulders drop, take a slow breath, and let's begin our slow drift through the story of an interstellar visitor that left us a gift we didn't expect. There's nowhere you need to be. Just listen and let the story unfold. The universe has time. Tonight, so do we. Let's begin where all good mysteries begin, with the moment we first encountered something unusual. On the 19th of November, 2020, a telescope system in Hawaii detected a faint moving object. The Atlas survey, short for Asteroid Terrestrial Impact Last Alert System, was doing its nightly scan of the sky when it recorded something that didn't quite fit the expected patterns. The detection itself was unremarkable at first glance. Atlas finds moving objects constantly. Most are asteroids from our own solar system, small rocky bodies that orbit the Sun between Mars and Jupiter, occasionally wandering into the inner solar system. Some are comets. Icy visitors from the distant reaches beyond Neptune. The sky is full of such objects, and Atlas catalogues them methodically, night after night. But this object was different. Within days of discovery, as more telescopes turned their attention to it, and more data accumulated, astronomers realized they were looking at something special. The orbit was wrong, or rather, it was exactly right for something extraordinary. The calculations showed that this object wasn't bound to our solar system at all. It was moving too fast on a trajectory that would carry it back out into interstellar space. This was 3I/ATLAS, the third confirmed interstellar object passed through our solar system. The designation tells a story in itself. The 3I means third interstellar. The first was Oumuamua, discovered in 2017, which became famous for its unusual cigar-like shape and mysterious acceleration. The second was 2I/Borisov, found in 2019, a more conventional comet that behaved exactly as expected. And now this, 3I/ATLAS, arriving from the space between stars. The object brightened as it approached the Sun, reaching its closest point in early 2021. During those weeks, observatories around the world studied it intensively. They measured its brightness, tracked its motion, analysed its light through spectroscopes to determine composition. Every clear night was an opportunity to gather more data, to understand this visitor from beyond. Some observations suggested weak cometary activity. There were hints of a faint coma, a thin atmosphere of gas and dust surrounding the nucleus. Other observations were less conclusive. The data was ambiguous enough that scientists debated whether it was truly a comet or merely an asteroid. This ambiguity became a defining characteristic of 3I/ATLAS. It existed in the grey zone between classifications, neither fully one thing nor another. By March of 2021, the object had passed perihelion and was heading back out. It grew fainter with each passing week as it moved away from the Sun and Earth. By April, only the largest telescopes could still detect it. By May, it had faded beyond practical observability. The intensive observation campaign ended. Papers were written, debates continued, but the physical act of watching 3I/ATLAS was over, or so everyone thought. The scientific community moved on to other objects. Other discoveries. 3I/ATLAS became an entry in catalogues, a topic of occasional discussion, a reference point for understanding interstellar visitors. It was receding into the outer solar system at 34 kilometers per second, well on its way back to the interstellar medium. Within a few years, it would be beyond Neptune's orbit. Within decades, beyond the Oort cloud. Within centuries, light years away. The story, it seemed, was complete. We had detected an interstellar object, studied it as best we could, and watched it leave. What more could there be? As it turned out, quite a lot. After 3I/ATLAS faded from view in mid-2021, the astronomical community turned its attention elsewhere. This is natural and necessary. The sky is vast and new discoveries happen constantly. Telescopes have limited time, and every night of observation must be carefully allocated. You cannot watch everything at once. Choices must be made. During the years that followed, astronomy continued its steady march forward. New asteroids were discovered and catalogued. Comets appeared from the outer solar system, brightened as they approached the Sun, then faded again. Exoplanet researchers added hundreds more worlds to the catalogue of planets orbiting other stars. Gravitational wave detectors recorded collisions between black holes billions of light years away. The James Webb Space Telescope, launched in December of 2021, began returning spectacular images of distant galaxies and nebulae. In this context, 3I/ATLAS was a footnote. An interesting footnote, certainly. Papers were published analysing the data collected during its passage. Researchers debated its classification, proposed models for its composition, discussed what it might tell us about planetary systems beyond our own. But there were no new observations. The object was gone, too faint and too distant to study further with existing technology. Some astronomers continued to think about interstellar objects in general. The field was growing. With 3 confirmed detections, researchers could begin to do statistics, to estimate how common such visitors might be, to predict how many more we might find in coming years. Proposals were written for dedicated surveys that would search specifically for interstellar interlopers. Missions were designed, at least on paper, that could rapidly respond when the next visitor was detected, perhaps even rendezvousing with it for close-up study. But 3I/ATLAS itself seemed to belong to the past. Its trajectory was well established. We knew where it was going, out, into the void between stars. We knew we would never see it again. Its distance from the Sun was increasing by nearly 3 million kilometers every day. By late 2023, it was approximately twice as far from the Sun as Jupiter, somewhere in the region where the asteroid belt gives way to the outer solar system. Yet data from those weeks of intensive observation in early 2021 continued to exist. It sat in archives, on hard drives, in databases maintained by observatories and research institutions. This is one of the beautiful aspects of modern astronomy. Observations are preserved. They can be re-examined later, analysed with new techniques, compared against new discoveries. Several research groups maintained an interest in 3I/ATLAS, even after direct observation ceased. They worked on refining the orbital calculations, extracting every bit of information possible from the existing data. They developed models for what the object might be made of, how it might have formed, where it might have originated. They compared it to Oumuamua and 2I/Borisov, looking for patterns and differences. One such group was particularly interested in the orbital dynamics. They were trying to work backward to trace 3I/ATL-AS's path through the galaxy before it entered our solar system. This is extraordinarily difficult. The farther back you trace, the more uncertain the path becomes. Small errors in measuring the current orbit compound over time. And the object's motion is influenced not just by the sun and planets, but by the gravitational field of the galaxy itself, by the collective pull of billions of stars. Still, they persevered. Using the best available data and sophisticated computer simulations, they traced possible trajectories. Where might the object have come from? When did it enter interstellar space? Could they identify a source? A specific star system that might have been its home? The answers were frustratingly vague. The object could have come from any of thousands of nearby stars or from much farther away. It had likely been travelling through interstellar space for hundreds of thousands of years, possibly millions. Its path had been bent and twisted by countless gravitational influences. The galaxy rotates, stars move. Everything is in motion over such timescales. Tracing backward with certainty was impossible, but in the process of this work in late 2023, they noticed something odd, something that didn't fit the models, something that suggested the story of 3I/ATL-AS wasn't quite as finished as everyone had assumed. What they noticed was subtle, it wasn't dramatic. It wasn't obvious. In fact, it took sophisticated analysis and careful comparison of multiple datasets to even see it. But once seen, it couldn't be unseen. The trajectory of 3I/ATL-AS, as it receded from the Sun, was not quite what it should have been. Remember, we can predict orbital motion with extraordinary precision. Give us the position and velocity of an object at one moment, along with knowledge of all the gravitational influences acting on it, and we can calculate where it will be at any future time. For objects in our solar system, these predictions are tested constantly and proven accurate. We can predict planetary positions decades in advance, precise enough to plan space missions. For 3I/ATL-AS, the predictions were based on observations from late 2020 through early 2021. Hundreds of measurements from dozens of telescopes worldwide. The orbit was well determined. The uncertainties were small. We knew, or thought we knew, exactly where the object was and where it was going. But when the research group checked recent astrometric data, precise measurements of stellar positions, they found something unexpected. There are surveys that constantly measure star positions, tracking how they move across the sky. This is important for understanding stellar motion, for detecting wobbles that might indicate planets, for a dozen other reasons. In late 2023, one such survey had incidentally captured a region of sky where 3I/ATL-AS should have been. The object wasn't visible in the images. That was expected. By late 2023, it was far too faint to detect directly in most surveys, but the researchers realized they could use the star field itself as a reference. If a massive object passes in front of distant stars, its gravity bends the light from those stars, causing tiny shifts in their apparent positions. This effect, called gravitational microlensing, is well established and has been used to detect everything from planets to black holes. They weren't expecting a gravitational microlensing signal from 3I/ATL-AS. The object was far too small. Its gravity would be negligible. But they were interested in the star field for another reason: photometric monitoring. They wanted to check if any stars in that region had changed brightness unexpectedly, which might indicate something passing in front of them, casting a shadow. What they found was surprising. The data showed subtle irregularities in that region of sky during a period in mid-2023. Not one star, but several, had shown brief, minor fluctuations in brightness over a span of weeks. The fluctuations were tiny, barely above the noise threshold, Individually, each could be dismissed as instrumental error or statistical fluke, but collectively they formed a pattern. The pattern suggested something was there. Something small, something faint, something that occasionally occulted stars, passed in front of them, briefly blocking their light. But 3I/ATLAS should have been long gone from that region by mid-2023. According to the orbital calculations, it should have been much farther away. At first, they assumed an error in their analysis. Perhaps the stellar data was corrupted. Perhaps the pattern was coincidence. Perhaps they'd made a mistake in calculating where 3I/ATLAS should be. They checked and rechecked. They examined the data from different angles. They consulted with colleagues. But the pattern persisted, and when they carefully reconstructed the timing and geometry, a startling possibility emerged. The fluctuations were consistent with something accompanying 3I/ATLAS. Not the object itself, but something else. Something that had been travelling with it. But in a slightly different orbit. Something that we hadn't detected during the original observation campaign, because it was too small or too dark or too close to the main object. 3I/ATLAS, it seemed, had not arrived alone. Or perhaps more accurately, it had not left alone. Something had come with it, or something had been left behind, and we were only now noticing. Science thrives on verification. A single surprising result, no matter how carefully analysed, isn't enough. It must be confirmed, preferably by independent researchers using different data and different methods. When the team first noticed the anomalous stellar fluctuations, they knew they couldn't simply announce a discovery. They needed to be certain. The first step was to check for alternative explanations. Could the brightness changes be caused by the stars themselves? Some stars are variable, changing brightness naturally over time. But these stars had been monitored for years, and none had shown variability before. Could it be instrumental? Perhaps a problem with the telescope or detector. But the fluctuations appeared in data from multiple telescopes, making instrumental error unlikely. Could it be asteroids from our own solar system, coincidentally passing through the same region of sky? This seemed more plausible. The solar system contains millions of asteroids, and occasionally one passes in front of a background star. But the probability of multiple asteroids independently creating this specific pattern was vanishingly small, and the timing was suggestive. The fluctuations occurred in the region where 3I/ATLAS had been months earlier. They needed more data. But there was a problem. You can't go back in time. The fluctuations had occurred in mid-2023, and it was now late 2023. They couldn't re-observe those specific events. What they could do was predict where this hypothetical companion object might be now and look for it there. This required some assumptions and calculations. If something had been travelling with 3I/ATLAS, what orbit might it have? The stellar occultation data provided clues about position at specific times, but not a complete trajectory. The researchers modelled various possibilities. Perhaps it was a fragment that had broken off from the main object. Perhaps it was a small moon or binary companion. Perhaps it was debris in a trailing orbit. Each possibility implied different locations for the object in late 2023. They calculated a range of potential positions and submitted urgent proposals for telescope time. Observing time on major telescopes is allocated months in advance, but there are provisions for targets of opportunity, unexpected discoveries that warrant immediate attention. Their proposal was convincing enough to secure a few nights on a large telescope in Chile. The observations were scheduled for December 2023. The team was nervous. If they found nothing, it would suggest their anomaly was spurious, a pattern seen in noise. If they found something, it would confirm that 3I/ATLAS had indeed not been alone. The implications would be significant, not just for understanding this specific object, but for how we think about interstellar visitors in general. The nights arrived, the weather cooperated. The telescope pointed to the predicted coordinates and began exposing, collecting photons from that distant region of space. Each exposure took several minutes, long enough to gather sufficient light from faint objects. The images were processed in near real time, compared against reference star fields to identify anything that moved or appeared unexpectedly. For 2 nights, they found nothing. The predicted region was empty, or at least contained nothing unusual. Disappointment began to set in. Perhaps they'd been wrong. Perhaps the orbital calculations were off. Perhaps the whole thing had been a wild goose chase. But on the 3rd night, there was a detection. Not where they'd expected, but close. A faint smudge, barely distinguishable from background noise, that appeared in multiple exposures and moved slightly between them. The motion was consistent with an object in the outer solar system, moving outward at high velocity. And the trajectory, when calculated, was consistent with having been near 3I/ATLAS in early 2021. The discovery was thrilling but raised immediate questions. What was this object? How big was it? What was it made of? And most importantly, what was its relationship to 3I/ATLAS? The observations provided a position and motion, but little else. The object was too faint for detailed spectroscopy. Its brightness suggested it was small, perhaps tens of meters across at most, assuming a typical reflectivity. But it was there. It was real. Something had indeed accompanied 3I/ATLAS through our solar system, and we were only now discovering it nearly 3 years after the main object's closest approach. The question was, what happened next? With confirmation that something was there, the research effort intensified. More telescope time was secured. Other research groups, hearing about the discovery, contributed their own observations. Within weeks, a clearer picture began to emerge. Though many mysteries remained, the object was small. Based on its brightness and assuming it reflected sunlight like a typical asteroid or comet nucleus, researchers estimated it was between 20 and 50 meters across. That's small by astronomical standards, roughly the size of a house or a small apartment building. But for an object in the outer solar system, too far from Earth for radar observation, even determining size with this level of precision was an achievement. It was dark. The albedo, the fraction of sunlight reflected, appeared to be low, perhaps 10% or less. This suggested a surface covered in dark material, possibly organic compounds or radiation-processed minerals. Many objects in the outer solar system are dark, so this wasn't particularly surprising. But it did mean the object was harder to see than a bright icy surface would be. The orbit was the most interesting aspect. By combining the December 2023 observations with the reanalyzed stellar occultation data from mid-2023, and even going back to the original 3I/ATLAS observation campaign to look for missed signals, researchers reconstructed the object's trajectory. What they found was remarkable. The object was indeed following 3I/ATLAS, but not closely. It was in a similar orbit, heading outward from the Sun at comparable velocity, on a trajectory that would also carry it into interstellar space. But its path was slightly different. The two objects were separated by millions of kilometers and diverging slowly. They had been closer in early 2021, perhaps within hundreds of thousands of kilometers, but the orbits weren't identical. This suggested several possibilities. Perhaps the two objects had originated together, both ejected from the same planetary system in the distant past. Perhaps they were fragments of a larger parent body that had broken apart. Perhaps one had captured the other during a chance encounter in interstellar space, only to be separated again by the Sun's gravity during their passage through our solar system. Each scenario had implications. If they originated together, it might mean interstellar objects sometimes travel in groups, like asteroids in a family, or comets in a stream. If they were fragments, it raised questions about what might cause such a breakup. Collisions are rare in interstellar space, where densities are extremely low. But thermal stress or rotational spin-up could potentially fracture a weak body. The capture scenario was intriguing but seemed less likely. The probability of two interstellar objects encountering each other and being gravitationally bound is extraordinarily small. Interstellar space is vast and mostly empty. Objects might pass within light years of each other and never interact. To have two objects travelling together suggested a common origin. Researchers gave the new object a provisional designation, 3I/ATLASB, indicating it was the secondary component of the 3I/ATLAS system. Some preferred to call it a companion rather than a fragment, keeping the question of origin open. Others speculated it might be debris, material shed from 3I/ATLAS during its passage near the Sun. If it was debris, that would have important implications. It would mean 3I/ATLAS had been more active than the ambiguous observation suggested. Comets shed material constantly when they're near the Sun. Ice sublimates, dust is released, and sometimes larger chunks break off. If 3I/ATLAS had shed this companion during perihelion passage, it would strongly support the comet hypothesis for the main object. But there were problems with this idea. The companion's orbit didn't quite match what you'd expect from debris shed near perihelion. Ejected material typically follows specific trajectories determined by the timing and velocity of ejection. The companion's orbit was similar to 3I/ATLAS's, but not in the way debris would be. The mystery deepened. We had found something unexpected, confirmed its existence, and characterized it enough to know it was real and significant. But understanding what it truly was, and how it related to 3I/ATLAS, would require more work. And there was another question looming. If there was one companion, might there be more? Had 3I/ATLAS left behind a trail of objects that we simply hadn't noticed yet? Once 3I/ATLASB was confirmed, researchers faced an obvious question. Had we actually observed it during the original 2020 to 2021 observation campaign but somehow missed it? This happens more often than you might think in astronomy. Telescopes capture enormous amounts of data, and not everything is analysed immediately or thoroughly. Sometimes discoveries hide in plain sight, waiting for someone to look at the data from a new angle. The research team went back to the archives. They retrieved images from every telescope that had observed 3I/ATLAS during its passage through the inner solar system. This included data from professional observatories, from automated survey telescopes, and even from skilled amateur astronomers who had photographed the object. All told, there were thousands of images spanning several months. Searching through this archive was not straightforward. The images were taken at different times with different telescopes, under different conditions. Each had its own characteristics, its own noise patterns, its own limitations, and the target, 3I/ATLASB, would have been extraordinarily faint, probably only a few pixels across at most. Easily lost in the background. Modern image processing helped. The team used techniques called stacking and shift and add, where multiple images are aligned and combined to bring out faint signals. When you add images together, real objects appear brighter while random noise averages out. This is especially effective for moving objects. You shift each image to account for the object's motion, then add them up. The object becomes visible while background stars trail and blur. They started with images from late January and early February 2021, when 3I/ATLAS was near its brightest, and presumably when any companion would also be most visible. They processed sets of images from each observatory separately, looking for faint streaks or smudges that move consistently with an orbit similar to 3I/ATLAS. The work was tedious. Each processing run took hours of computer time. Most revealed nothing, but slowly, tentatively, signals began to emerge. In a set of images from a telescope in Chile, there was a faint streak, barely above the noise threshold, offset from 3I/ATLAS by a specific angular distance. In images from a telescope in Hawaii taken a week later, there was another faint signal in a position consistent with the first detection. None of these individual detections would have been convincing on their own. Each could be dismissed as noise, as a cosmic ray hit on the detector, as a processing artifact. But together they formed a pattern. When plotted according to time and position, they traced out an orbit, and that orbit matched, within uncertainties, the orbit later calculated from the 2023 observations. 3I/ATLAS-B had been there all along. We had photographed it dozens of times during the original observation campaign, but it had been too faint, too close to the much brighter primary object, or too easily confused with background stars. No one had noticed it at the time. The discovery had been hiding in the data for nearly 3 years. This revelation was both exciting and humbling. Exciting because it meant we now had data spanning a much longer time baseline, allowing for better orbital calculations and potentially more information about the object's properties. Humbling because it showed how easy it is to miss things, even when you're looking carefully. It also raised questions about methodology and resources. Astronomical surveys generate petabytes of data every year. Not all of it is analysed to the deepest possible level. There's simply not enough time or person power. Automated algorithms flag obvious things and humans follow up on those. But subtle signals, faint objects, unexpected phenomena, these can slip through. How many other discoveries might be hiding in archival data? How many unusual objects have we photographed but not recognised? The thought is both thrilling and slightly overwhelming. There's gold in those archives, if only we knew how to find it efficiently. Some researchers are developing machine learning algorithms to help. Neural networks can be trained to recognise patterns that humans might miss. They can sift through vast data sets looking for anomalies. But this is still a developing field. The algorithms are good but not perfect. They sometimes flag noise as signals, or miss real signals that don't quite match their training data. For now, the discovery of 3I/ATLAS-B relied on human intuition and effort. Someone had to think to look for it. Someone had to develop the processing techniques to bring it out of the noise. Someone had to have the patience to work through thousands of images. This is how much of science still works, not through automated discovery, but through careful, thoughtful effort by dedicated people. With better data on 3I/ATLAS-B's orbit, and the knowledge that it had been travelling with the primary object for an extended period, researchers began to seriously consider a specific hypothesis, that the two objects formed a binary system. That is, they were gravitationally bound to each other, orbiting their common centre of mass while both orbited the Sun. Binary asteroids are not uncommon in our solar system. Roughly 15% of near-Earth asteroids are binaries, and the fraction may be even higher in other populations. These systems form through various mechanisms. Some are fragments from collisions, some are formed when a fast-rotating object sheds material that goes into orbit. Some may be capture events where two objects' paths brought them close enough to become bound. Binary comets are rarer but known to exist. The most famous example is probably Comet 67P/Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission. That comet has a distinctive two-lobed shape, strongly suggesting it formed from two separate objects that gently collided and merged. Other comets have been observed to split, creating temporary binary systems before the components drift apart or one disintegrates. Could 3I/ATLAS and its companion be a binary system? The orbital data suggested it was possible. The two objects were separated by a few 100,000 kilometres during the observation period in early 2021. For reference, that's about the same as the distance from Earth to the Moon. At such separation, gravitational binding between small objects is tenuous. The Sun's gravity dominates. But if the objects were moving at just the right relative velocity, they could remain loosely bound. Researchers ran simulations. They modelled the gravitational interactions between the two objects, accounting for the Sun's gravity, the gravity of the planets, and even more subtle effects like radiation pressure and outgassing forces if either object was active. The simulation showed that a bound binary configuration was dynamically possible, but only under specific conditions. The two objects would need to have had very similar velocities when they entered the solar system. If their relative velocity was too high, the sun's tidal forces, the differential pull of gravity across the system, would tear them apart. This is called the Roche limit, the distance at which tidal forces overcome the object's mutual gravity. For loosely bound, small objects, this limit is relatively large. The fact that 3I/ATLAS and its companion survived passage through the inner solar system without being torn apart suggested either they were more tightly bound than the separation implied, perhaps they had been closer earlier and were only now drifting apart, or they were not truly bound at all but merely travelling on similar paths. Distinguishing between these scenarios required precise measurements of the relative velocity. How fast were the objects moving apart? If they were gravitationally bound, the separation should change in a specific way, governed by orbital mechanics. They might be in an elliptical mutual orbit, sometimes closer and sometimes farther, or they might be on a hyperbolic trajectory, slowly separating forever. The data was not quite good enough to determine this definitively. The observations spanned only a few months, and the change in separation over that time was small compared to the overall distance. With more time, the answer would become clear. If the separation continued to increase linearly, they were not bound. If it varied in a periodic or more complex way, they might be. There was also the question of origin. If 3I/ATLAS and its companion were a binary, had they formed as a binary in their original planetary system? Or had they become bound during their journey through interstellar space? The latter seemed unlikely. The probability of capture in interstellar space is extraordinarily low. But the former raised interesting questions about planet formation and how binaries form. In our solar system, binaries seem to form after the initial planet formation stage, through collisions or rotational spin-up. But maybe in other systems, conditions favour binary formation earlier. Maybe some regions of protoplanetary disks produce binary planetesimals naturally. Each planetary system has its own history, its own conditions. Studying objects from other systems could reveal diversity we haven't imagined. The binary hypothesis was attractive because it explained the observed association between the two objects. But like all hypotheses, it needed to make testable predictions. What would we expect to see if they were truly bound? What observations could prove or disprove the idea? These questions guided the next phase of research. Science progresses by considering alternatives. Even when one hypothesis seems promising, responsible researchers must ask, what else could explain the observations? For 3I/ATLAS and its companion, several alternative explanations deserve consideration. The first alternative was the fragment hypothesis. Perhaps 3I/ATLAS-B was not a separate object that had always accompanied the primary, but rather a piece that broke off during the passage through our solar system. Comets do this occasionally. The sun's heat can create thermal stresses, causing cracks to form and propagate. Rotational forces, if the nucleus is spinning, can pull a weakly bound object apart. Tidal forces, though usually only significant for very close encounters, could play a role. If fragmentation had occurred, when might it have happened? The most likely time would be near perihelion, when the object was closest to the sun and experiencing the most intense heating. This occurred in early January 2021. Observations from this period could potentially show evidence of fragmentation, a sudden change in brightness, an asymmetric coma, or direct imaging of multiple components. Researchers went back to the data again, now looking specifically for signs of splitting. They examined light curves, graphs showing brightness over time, for any sudden changes. They looked at high-resolution images for any hint of multiple nuclei. They analysed the dust and gas distribution for asymmetries that might indicate material being lost from one side. The evidence was ambiguous. There were no dramatic changes that screamed, quote, one, but there were subtle features in some images that could potentially be interpreted as evidence of activity or structural changes. The problem was that the observations were not continuous. There were gaps of days or even weeks between some observations. If fragmentation occurred during a gap, we might have missed it. A second alternative was the coincidence hypothesis. Perhaps 3I/ATLAS and its companion were not related at all. Perhaps they just happened to be travelling on similar trajectories through our solar system at the same time. This seems incredibly unlikely. Interstellar space is vast, and the probability of two independent objects passing through at nearly the same time and place is astronomically small. But unlikely is not impossible. Statistical reasoning requires us to consider how improbable something must be before we reject it entirely. In a galaxy with billions of stars and presumably trillions of rogue objects, coincidences can happen. Maybe we're the beneficiaries of exceptionally rare luck, having two interstellar objects pass through simultaneously. The problem with the coincidence hypothesis is that it doesn't explain the similarity in their orbits. Not only were they in the same general region of space, but their velocities and trajectories were remarkably similar. For truly independent objects, you'd expect more diversity in orbital parameters. The similarity suggested a common origin of some kind. A third alternative was the debris stream hypothesis. Perhaps both objects, and possibly others we haven't detected yet, were part of a stream of debris from a single catastrophic event. Imagine a large comet or asteroid that disintegrated, perhaps due to a collision in its home system or from passing too close to a star. The fragments would initially move on very similar trajectories, forming a stream. Over time, slight differences in velocity and gravitational perturbations would spread the stream out. But it could remain coherent for millions of years. If this were true, we might expect to find more objects in similar orbits. The stream could be sparse, one object every few million kilometres, but it would be there. This became a target for future searches. If more companions to 3I/ATLAS were discovered, all on similar trajectories, it would strongly support the debris stream hypothesis. Each alternative explanation had strengths and weaknesses. The fragment hypothesis explained the association, but required a fragmentation event we didn't directly observe. The coincidence hypothesis required accepting extraordinary improbability. The debris stream hypothesis was appealing, but required additional objects to be found. And then there was the binary hypothesis from the previous chapter, which had its own requirements and predictions. Science is often like this. Multiple explanations fit the data, each with its own assumptions. Progress comes from finding observations that can distinguish between them, that can rule out some possibilities and support others. In the case of 3I/ATLAS and its companion, definitive answers would require more data. Continued observation might reveal whether the objects were gravitationally bound. Spectroscopic analysis, if ever possible, might show whether they had the same composition. Discovery of additional companions would transform our understanding. But for now, in the absence of perfect information, researchers had to work with uncertainty, considering all possibilities and being honest about what they didn't know. Orbits are stories written in mathematics. Every trajectory through space carries information about the forces that shaped it, the origins of the moving object, the environment it has passed through. For 3I/ATLAS and its companion, careful analysis of their orbital parameters revealed hints about their shared history. Both objects were on hyperbolic orbits with respect to the Sun. This means they were moving faster than escape velocity. Gravitationally, they were just passing through, never to return. Their eccentricities, a measure of how elongated an orbit is, were greater than 1, which mathematically defines a hyperbolic trajectory. A circular orbit has eccentricity 0. Earth's slightly elliptical orbit has eccentricity of about 0.017. Comets in our solar system might have eccentricities of 0.9 or higher. but eccentricities greater than 1 are only possible for objects not bound to the Sun. The specific eccentricity of 3I/ATLAS was approximately 1.15. The companion's eccentricity was similar, about 1.13. This similarity was noteworthy. If the objects had independent origins, you'd expect more variation. The fact that their eccentricities were so close suggested they had experienced similar gravitational influences over their lifetimes. The orbital inclinations, the angle between the orbit and the plane of the solar system, were also similar. Both objects had inclinations around 50 degrees. They weren't coming in along the ecliptic, the plane where planets orbit, but from well above it. This wasn't unusual for interstellar objects which can approach from any direction. But again, the similarity between the two objects was striking. Researchers calculated what's called the relative velocity at infinity. This is a measure of how fast the objects were moving relative to the Sun when they were very far away, before the Sun's gravity accelerated them inward. For 3I/ATLAS, this velocity was about 34 kilometers per second. For the companion, it was about 33.5 kilometers per second, remarkably similar. These similarities painted a picture. Whatever the relationship between the two objects, they had spent a long time travelling together. They had entered the solar system from nearly the same direction, at nearly the same speed, on nearly the same trajectory. The Sun's gravity had pulled them both inward, accelerated them both to high speeds at perihelion, and was now flinging them both back out into interstellar space. And through all of this, their paths remained similar. Dynamicists, specialists in orbital mechanics, ran backward integrations. They took the current orbits and calculated backward in time, accounting for the gravity of the Sun and planets, trying to determine when and where the two objects might have been closer together. These calculations are tricky because small uncertainties in the current orbit lead to large uncertainties when you integrate far into the past. But patterns emerged. Several 100,000 years ago, give or take a factor of 2, the two objects appeared to have been much closer together, perhaps only thousands of kilometers separated, rather than hundreds of thousands. This suggested that if they were now separating, they had been doing so for a long time. The separation velocity was tiny, perhaps only a few centimeters per second, but over hundreds of thousands of years this adds up. Alternatively, if they were bound in a long-period mutual orbit, they might have been at a close approach point hundreds of thousands of years ago and were now near their maximum separation. The orbital period, the time to complete one mutual orbit, would be measured in centuries or millennia. We would never observe a complete orbit, but we could infer its existence from the patterns in the data. The gravity from the Sun and planets also left marks on the orbits, as the objects passed Jupiter, for instance. The giant planet's gravity slightly altered their trajectories. By comparing the predicted effects to the observed orbits, researchers could check the consistency of their models. Everything had to fit together. The observations, the dynamics, the forces. One particularly interesting aspect was the orientation of the orbits. In orbital mechanics, there's a parameter called the longitude of ascending node, which describes where the orbit crosses a reference plane. For 3I/ATLAS and its companion, these values were nearly identical. This means they crossed the plane of the solar system at nearly the same point. It's yet another similarity that suggests a common history. All of this orbital analysis supported the idea that these objects were related. Whether they were binary companions, fragments of a common parent, or members of a debris stream, they had clearly travelled together for a very long time. They were a pair, linked by history and trajectory, visitors from beyond our solar system who arrived together and would leave together, slowly drifting apart but still connected by the paths they followed through the void. Understanding 3I/ATLAS and its companion was hindered by a fundamental challenge. They were faint and getting fainter. By late 2024, both objects were deep in the outer solar system, far beyond Jupiter's orbit, receding at tens of kilometres per second. Only the largest telescopes on Earth could detect them at all, and even then, just barely. This presented practical difficulties. Telescope time is precious. There are always more proposals for observations than there are available nights. To secure time, researchers must make a compelling case that their target is important and that their observations will yield scientifically valuable results. For objects as faint as 3I/ATLAS and its companion, there was real question about what could be learned. Brightness measurements were still possible. By tracking how the objects faded over time, researchers could learn about surface properties and shape. If an object is rotating and has an irregular shape, its brightness varies periodically. By measuring this light curve, you can determine rotation period and get hints about the shape. For 3I/ATLAS, this had been attempted during the original observation campaign, but the data was noisy and no clear period emerged. Now, with the object fainter and more distant, getting good light curves was even harder. Each data point required long exposures, sometimes an hour or more, to collect enough photons, and you needed many data points to cover a full rotation, which might be hours or days. The observations demanded patience and dedication. Spectroscopy, spreading light into its component colours to determine composition, was essentially impossible at this distance. The objects were simply too faint. Even the most sensitive spectrographs on the largest telescopes couldn't collect enough light to produce a useful spectrum. All we could measure was how much light the objects reflected overall, not what that light could tell us about composition. Colour photometry was still feasible. By measuring brightness through different filters, blue, green, red, infrared, you could determine the colour of the object. Colour provides some information about surface composition. Icy surfaces tend to be neutral or slightly blue. Rocky surfaces might be redder. Organic rich surfaces are often very red. But colour alone doesn't give you a unique answer. Many different materials can produce similar colours. For both 3I/ATLAS and its companion, colour measurements suggested they were relatively neutral or slightly red. This was consistent with many possibilities: rocky material, carbonaceous compounds, radiation-processed ices. It didn't narrow things down much. There was also the question of shape. Was 3I/ATLAS spherical, elongated, irregular? The light curve data, such as it was, suggested some degree of irregularity. The brightness varied over time, though not dramatically. This could mean the object was slightly elongated, or had bright and dark patches on its surface. For the companion, there wasn't enough data to say anything definitive about shape. Sizes remained uncertain. Without knowing the albedo, how reflective the surface was, you couldn't convert brightness to size with precision. A small, bright object looks the same as a large, dark object. Researchers made educated guesses based on typical values for comets and asteroids, but these were just guesses. Some researchers proposed using occultations, watching the objects pass in front of background stars, to measure sizes directly. When an object blocks a star's light, even briefly, you can measure its shadow and determine its size quite accurately. But orchestrating an occultation observation requires knowing the object's position very precisely and being in the right place on Earth at the right time. For faint, distant objects, this is challenging. Despite all these difficulties, observations continued sporadically. A few nights here, a few nights there, whenever telescope schedules and conditions allowed. Each observation added a little more information. The orbits became more precise. The brightness curves grew slightly longer. Slowly, incrementally, understanding improved. But there was a clock ticking. Every day the objects moved farther away and became fainter. There would come a point, perhaps in 2026 or 2027, when even the largest telescopes could no longer detect them. They would fade into the background, indistinguishable from the countless faint galaxies that populate deep images of the sky. And then direct observation would end forever. This created a sense of urgency. If important observations were to be made, they had to happen soon. If questions were to be answered, the data had to be collected while it was still possible. Researchers raced against time and the inverse square law of light, which dictates that brightness decreases with the square of distance. The objects were winning that race, slowly disappearing into the vast dark from which they'd come. The discovery of 3I/ATLAS-b had implications that reached beyond the two objects themselves. It changed how astronomers thought about interstellar visitors in general. If one interstellar object could have a companion, others might too. If we missed this companion for nearly 3 years, what else might we be missing? Consider the implications for population estimates. When astronomers try to figure out how many interstellar objects pass through the solar system, they use detection statistics. They count how many we've found, estimate how many we've missed based on the sensitivity of surveys, and extrapolate to the total population. But these calculations assume we're detecting all significant objects in a given system. If interstellar objects commonly have companions, and those companions are often too faint or too close to the primary to detect easily, then our population estimates might be too low, perhaps significantly too low. Maybe interstellar space is more crowded than we thought, populated not just by solitary wanderers but by pairs and groups. This would make sense from a dynamical perspective. When objects are ejected from planetary systems, the ejection process doesn't always involve a single object. Sometimes multiple objects are scattered simultaneously during a close encounter with a giant planet. Sometimes a large body breaks up under tidal stress, creating fragments that are ejected together. These related objects would initially travel on similar paths. Over time, slight differences in velocity and gravitational perturbations would spread them apart. But for the first hundreds of thousands or millions of years, they might remain loosely associated. From our perspective, observing them at one moment in their long journey, they could appear as binary systems or companions. The possibility of binary interstellar objects also affected predictions for future surveys. The Vera C. Rubin Observatory, which will begin full operations in the mid-2020s, is expected to discover many more interstellar visitors. Current estimates suggest perhaps 1 to 10 per year. But if a significant fraction of these are binaries, the actual number of individual objects could be higher. This also had implications for mission planning. Several space agencies and research groups have proposed missions to intercept and study interstellar objects up close. These missions face enormous challenges. The objects move fast, they're detected late, and matching velocities requires huge amounts of fuel. But if the target object has companions, the mission could potentially study multiple objects, greatly increasing scientific return. Imagine a spacecraft rendezvousing with an interstellar object and discovering it's a binary. The spacecraft could study both components, compare their properties, measure their mutual orbit, perhaps even land on both if it's ambitious enough. This would provide unprecedented insights into how these objects formed and evolved. There were also implications for the hazard these objects might pose. Earth gets hit by asteroids and comets from our own solar system occasionally. Most burns up in the atmosphere, but large impacts do happen and can be devastating. Interstellar objects moving at higher velocities would hit with more energy if they struck Earth. But they're also much rarer than local asteroids. If interstellar objects sometimes come in groups, does that change the risk? Probably not significantly. The objects are still rare, and space is still vast. The probability of Earth being hit by even a single interstellar object is extremely low. The probability of being hit by multiple objects from the same system is vanishingly small. But it's not zero, and for completeness, risk assessors had to consider it. From a broader perspective, the discovery reinforced something astronomers have known for a while. The universe is more complex and varied than our limited sample suggests. We've studied our own solar system in detail, but it's just one example. Other systems might be quite different. The objects they produce and eject might be different. Binary interstellar objects might be common elsewhere, even if they're rare or non-existent in our system. Every interstellar visitor is a gift, a sample from beyond our solar neighbourhood that teaches us about the diversity of planetary systems. With only 3 confirmed interstellar objects and counting as of late 2024, Oumuamua, 2I/Borisov, 3I/Atlas, and now 3I/ATLASB, we're still working with a tiny sample. But each one expands our understanding, each one challenges our assumptions. The field of interstellar object studies was still young, just entering its adolescence. The coming decades would bring many more detections, much better data, and hopefully some answered questions. But also, inevitably, new mysteries. That's how science works. Every answer breeds new questions. The existence of 3I/ATLAS and its companion, travelling together through interstellar space, provided a window into processes that happen in all planetary systems, including our own. Specifically, it told us about ejection mechanisms and how planetary systems evolve over time. When a planetary system forms, it begins with a protoplanetary disk, a flat, rotating cloud of gas and dust surrounding a young star. Within this disk, particles collide and stick together, growing from dust grains to pebbles to boulders to kilometre-sized planetesimals. Some of these planetesimals continue accreting material, eventually becoming planets. Others remain small, forming the population of asteroids and comets. But planet formation is a messy, chaotic process. Gravitational interactions between growing planets and smaller bodies lead to orbital changes. Some objects are sent inward toward the star. Others are flung outward, and some achieve escape velocity, leaving the system entirely. Jupiter, in our solar system, has been particularly effective at ejecting objects. Computer simulations of the early solar system show that for every object Jupiter scattered into the Sun, it ejected dozens into interstellar space. Over the solar system's 4.5 billion year history, Jupiter and the other giant planets have likely ejected trillions of comets and asteroids. The same process must happen in every planetary system with giant planets, and simulations suggest that some stars eject even more material than our Sun. Systems where giant planets migrate inward, moving closer to their star over time, are especially efficient ejectors. The planet's motion stirs up the small body populations, flinging objects in all directions. If 2 small bodies are ejected during the same dynamical event, the same close encounter with a planet for instance, they will initially have similar velocities and trajectories. They'll leave the system together, travelling through interstellar space on parallel paths. Over time, slight differences will cause them to drift apart, but for the first hundreds of thousands or even millions of years, they'll remain loosely associated. This is likely what happened with 3I/ATLAS and its companion. At some point in the distant past, in a planetary system perhaps hundreds of light years away, a gravitational interaction, maybe with a Jupiter-like planet, maybe with multiple planets, scattered these 2 objects. They were flung out of their home system at high speed, on trajectories that would never bring them back. For millennia, they travelled through the cold darkness of interstellar space. The distance between them gradually increased, but they remained on similar paths. They passed through molecular clouds, regions where new stars were forming. They felt the weak tug of the galaxy's gravitational field. They were bombarded by cosmic rays, but they persisted, 2 silent wanderers in the void. Eventually, by chance, their trajectories brought them to our solar system. They fell inward toward the Sun, accelerated by gravity, passed through perihelion, and are now heading back out. In a few thousand more years, they'll be light years away again, continuing their journey through the galaxy. Perhaps in 1,000,000 years they'll pass through another planetary system. Perhaps not. The galaxy is large, and stars are far apart. This story of ejection and wandering must be common. Every star with planets probably ejects material. The galaxy has been around for over 10 billion years, long enough for early generations of planetary systems to have formed, evolved, and ejected countless objects. Interstellar space is likely filled with these wanderers, most of them dark and cold and invisible, occasionally passing close enough to a star to be detected. Studying objects like 3I/ATLAS and its companion helps us understand not just other planetary systems, but our own history as well. The early solar system was more chaotic than it is today. Planet migrations, orbital resonances, and close encounters shaped the current architecture. Many objects were lost in the process. Some of those lost objects might still be out there, in the Oort cloud or even beyond, in loosely bound orbits that take them thousands of astronomical units from the Sun. Others were ejected entirely and are now interstellar wanderers like 3I/ATLAS. If we could somehow identify and study solar system objects that were ejected billions of years ago, they would tell us about conditions in the early solar system. Of course, we can't do that. Once ejected, objects become part of the galactic background, indistinguishable from objects ejected by other stars. But we can study the process in general by observing interstellar visitors. Each one is a sample from some planetary system's history, a relic of formation and dynamical evolution. The fact that 3I/ATLAS has a companion adds a layer to this story. It suggests that ejection events can scatter multiple objects simultaneously, and that these objects can remain associated for extraordinarily long times. This has implications for how we model planet formation and system evolution. It's another piece of the puzzle, helping us understand the complex dance of gravity, collision, and chaos that turns protoplanetary disks into mature planetary systems. Once 3I/ATLASB was discovered, an obvious question arose: were there more companions? If there was one, might there be others? Could 3I/ATLE be accompanied by a whole family of objects, a stream of debris spread out over millions of kilometres? This question motivated additional searches. Researchers went back to the archival data yet again, now looking not just for one companion but for multiple faint signals. They also planned new observations targeting regions of space where additional companions might plausibly be found based on orbital dynamics. The searches were challenging. Any additional companions would likely be even fainter than 3I/ATLAS, which was already barely detectable. They might be spread out over a large region of space, making targeted observations difficult. And there was the problem of distinguishing them from background asteroids and other solar system objects. Despite these challenges, the searches proceeded. Teams used different techniques. Some focused on archival data, applying machine learning algorithms to flag potential candidates. Others used statistical approaches, looking for overdensities of faint objects in regions associated with 3I/ATLAS. Still others secured new telescope time for dedicated searches. As of late 2024, the results were inconclusive. A few potential detections had been made, but none had been confirmed with sufficient observations to be certain. There were faint objects in the general region where companions might be, but were they truly associated with 3/ATLAS, or were they unrelated background sources? This ambiguity was frustrating but not surprising. Astronomy often works this way. Initial detections are tentative. Confirmation requires follow-up observations which may take months or years. And sometimes what looks like a detection turns out to be noise or a misidentified object. The possibility remained that 3I/ATLASB was the only companion. Perhaps the original ejection event had scattered just two objects, or perhaps there were once more, but they've since drifted too far apart to be detected as a group. Space is vast, and even objects that start out close together can become separated by huge distances over hundreds of thousands of years. There was also the possibility of very small companions. If 3I/ATLAS had been a comet and had shed dust during its passage through our solar system, the dust would now be spread along its orbit. Individual dust grains are far too small to detect directly, but collectively they might create a faint trail visible in sensitive images. Some researchers looked for this. They stacked images taken at different times, aligning them based on 3I/ATLAS's orbital motion, and searched for faint streaks or extended emission that might indicate a dust trail. The results were tantalizing but not definitive. There might be something there, a faint smudge along the expected trajectory, but it could also be noise or background artifacts. If a dust trail existed, it would be strong evidence that 3I/ATLAS had been an active comet. Comets shed dust when their ices sublimate. The dust persists in orbit, creating the spectacular tails we see from Earth and lingering streams that Earth sometimes passes through, creating meteor showers. An interstellar comet would behave similarly, leaving a trail of dust along its path. But detecting such a trail from an interstellar object is extraordinarily difficult. The dust would be sparse, spread over millions of kilometers. It would be illuminated by sunlight but faintly, and it would be mixed with zodiacal dust, the dust from comets and asteroids in our own solar system that fills the inner solar system and creates a faint glow called the zodiacal light. Some researchers propose that future missions might be able to detect and study interstellar dust directly. Spacecraft with sensitive dust detectors could measure the impact of individual dust grains. By analysing the composition and velocity of these grains, you could potentially identify those of interstellar origin. A few such grains have already been collected, either by spacecraft like Stardust or found in Earth's upper atmosphere. But confirming their interstellar origin is difficult. The question of additional companions remained open. It was possible that more would be found as search techniques improved and more data accumulated. It was also possible that 3I/ATLASB was unique, the only companion we'd ever detect. Either way, the discovery had opened a new line of inquiry. Astronomers now knew to look for companions when studying interstellar objects. Future visitors would be scrutinized more carefully, with an eye toward detecting any associated objects. This was one of the valuable lessons from the 3I/ATLAS system. Even when you think you've observed something thoroughly, there may be more to discover. Faint signals can hide in data. Companions can go unnoticed. The universe is full of subtleties that reward careful attention and persistent searching. The discovery and study of 3I/ATLASB showcased how modern astronomy functions as a global, collaborative enterprise. No single person or institution made all the observations or did all the analysis. The work involved dozens of researchers from multiple countries using data from telescopes around the world. This collaboration began with data sharing. The original observations of 3I/ATLAS from 2020 to 2021 had been made by many different telescopes. Some data was immediately public, posted to archives where anyone could access it. Other data remained proprietary for a period, giving the observing team time to analyse and publish results before releasing it publicly. When the first hints of a companion emerged in late 2023, the researchers who made the discovery contacted colleagues who had observed 3I/ATLAS during the original campaign. They asked for access to any data that might help confirm the companion's existence. Most researchers willingly shared their data, recognizing that scientific progress benefits everyone. This kind of collaboration is encouraged in astronomy, but not always easy to facilitate. Different telescopes use different data formats. Images might be processed differently. Calibrations might be done using different standards. Getting all this data into a common format for analysis requires effort and coordination. The Discovery team also reached out to currently operating surveys, asking them to check recent observations for any incidental captures of the region where 3I/ATLAS and its companion were located. Several surveys had indeed imaged that region, though the objects weren't recognised in real-time processing. By going back and reprocessing those images with the known positions of the objects, useful data was recovered. Communication happened through multiple channels. Email was common for direct collaboration. Astronomical telegrams, Brief notices distributed to the community about new discoveries or observations announced the companion's discovery and coordinates, allowing others to follow up. Papers were submitted to journals undergoing peer review before publication. Conferences provided opportunities for in-person discussion and debate. There were challenges. Coordinating across time zones meant that collaborators might be sleeping when you needed to discuss something. Language differences occasionally caused misunderstandings, though English has become the lingua franca of astronomy, for better or worse. Different institutional cultures and funding pressures sometimes created friction. But overall, the collaboration worked. The discovery was made, confirmed, and published within a reasonable time frame. Credit was shared appropriately, with authorship on papers reflecting the contributions of different team members, and the broader astronomical community benefited from the freely shared results. This collaborative model is increasingly important in astronomy. Individual researchers or small teams can't do everything themselves. Telescopes are too expensive, expertise too specialized, data sets too large. Success requires bringing together people with different skills, observers who know how to use telescopes effectively, data analysts who can extract signals from noise, theorists who can interpret results, software developers who build the tools everyone uses. The study of interstellar objects particularly benefits from collaboration because the objects are rare and fleeting. When one is detected, the community must mobilize quickly to observe it before it fades. This requires sharing information rapidly and coordinating observations across multiple sites. No single observatory can watch continuously. Earth rotates, weather interferes. Telescopes break. But with observatories spread around the world, continuous coverage becomes possible. There's also an element of trust in this process. Researchers must trust that collaborators will give proper credit, that shared data won't be misused, that preliminary results won't be leaked prematurely. Mostly, this trust is warranted. The astronomical community is generally collegial and respectful, but not always. There have been cases of disputes over credit, of data being used without permission, of rushed publications cutting out colleagues who deserved authorship. These issues are taken seriously. Professional organisations like the International Astronomical Union have codes of conduct and ethics guidelines. Journals have policies about authorship and data sharing. Most researchers try to do the right thing, to be generous with credit and transparent about contributions. The 3I/ATLAS collaboration was, by most accounts, an example of how things should work. Disputes were minimal, credit was shared appropriately, data was made public after an appropriate period, and the scientific community learned something new about the universe. That's the goal, advancing knowledge together, building on each other's work, creating a collective understanding that no individual could achieve alone. While professional astronomers studied 3I/ATLAS and its companion, the story also captured public imagination. Interstellar visitors have a natural appeal. They come from beyond our solar system, from mysterious origins, travelling for eons before briefly passing through our neighbourhood. They're exotic, romantic, evocative of science fiction while being real science. News outlets picked up the story. Articles appeared explaining the discovery, often with dramatic headlines. Some coverage was accurate and well-informed, written by science journalists who understood the nuances. Other coverage was sensationalized, emphasizing mystery and speculation over established facts. The public response was interesting. Social media discussions showed people were curious about the implications. Where did the objects come from? What were they made of? Could they be artificial? This last question appeared surprisingly often. The Oumuamua discovery in 2017 had sparked speculation about alien technology, partly because of its unusual shape and acceleration. Though this speculation was largely dismissed by scientists, it lingered in public imagination. For 3I/ATLAS, there was less speculation about artificial origins, probably because it seemed more comet-like and less anomalous than Oumuamua. But the discovery of a companion reignited interest. Were the two objects somehow connected intentionally? Was this evidence of extraterrestrial engineering? Scientists patiently explained why natural explanations were far more likely. Binary asteroids are common. Fragmentation happens. Debris streams are expected. There was no need to invoke intelligence to explain what was observed. The laws of physics and chance were sufficient. But the questions reflected something important. People want the universe to be interesting, to hold mysteries and surprises. The idea of visitors from other star systems, even if they're just rocks and ice, excites the imagination. It reminds us that we're part of a larger cosmic context, that our solar system is not isolated but embedded in a dynamic galaxy. Educational institutions used the discovery as a teaching opportunity. Planetariums created shows explaining interstellar objects. Science museums updated exhibits. Teachers incorporated the story into lesson plans, using it to discuss orbits, gravity, spectroscopy, and the scientific method. Amateur astronomers, though unable to observe the faint objects themselves, followed the story closely. Online forums buzzed with discussion. Some amateurs reprocessed publicly available data, trying their hand at finding additional companions or extracting information from images. This kind of engagement is valuable. It builds scientific literacy and connects people to the research process. There was also artistic response. Writers crafted stories imagining the object's origins, creating fictional narratives about the planetary systems that might have ejected them. Artists created visualizations, trying to depict what the objects might look like up close. Musicians even composed pieces inspired by the lonely journey of interstellar wanderers. This cultural response to scientific discovery is part of what makes astronomy special. Unlike some fields where results are purely technical and accessible only to experts, astronomy deals with questions that everyone can appreciate. Where did we come from? What's out there? Are we alone? These are ancient questions pondered by every human culture. Modern astronomy provides tools to actually investigate them. The media coverage and public interest also had practical effects. It made funding agencies more willing to support interstellar object research. It helped justify telescope time for related observations. It created momentum that could lead to future missions. When the public is engaged and excited, politicians and administrators take notice. Of course, sustaining public interest is challenging. News cycles move quickly. Initial fascination fades. Most people moved on to other topics after a few weeks, though a dedicated subset continued following developments. This is natural and expected. Not everyone can or should be deeply invested in every scientific story, but the initial spike of attention served its purpose. It reminded people that astronomy is an active, ongoing process of discovery. It showed that even well-studied objects can hold surprises, and it demonstrated that the universe continues to reveal new wonders to those who look carefully. For the researchers involved, public interest was both gratifying and sometimes overwhelming. Gratifying because it validated their work, showing that people cared about what they were doing. Overwhelming because media requests and public inquiries took time away from actual research. Balancing these demands is a skill that not all scientists possess or enjoy, but most saw it as part of the job. Science is publicly funded, at least in large part. The public has a right to know what their support produces, and there's a responsibility to communicate clearly and honestly. To explain not just the discoveries, but also the uncertainties, the process, the ongoing nature of scientific inquiry. Despite years of observation and analysis, many fundamental questions about 3I/ATLAS and its companion remained unanswered. This is not a failure of science. It's simply a reflection of the difficulty of studying small, distant, fast-moving objects with limited observing opportunities. Let's consider what we still don't know. First, the composition of the objects. Are they icy like comets or rocky like asteroids? The limited spectroscopic data didn't provide a definitive answer. The objects might be mixtures, with some ice and some rock in proportions we can't determine. They might have surface coatings, dust, organic compounds, radiation-processed materials that obscure their bulk composition. Without knowing composition, we can't fully understand their history. Ice-rich objects would have formed in the cold outer regions of their origin system, beyond the ice line where water can condense. Rocky objects might have formed closer to the star where temperatures were higher. Mixed composition could indicate formation in a transitional zone or subsequent evolution that altered the original composition. Second, the true nature of the relationship between the two objects. Are they gravitationally bound, orbiting their common centre of mass? Are they fragments of a larger parent body? Are they independent objects that happen to be ejected together? The observations are consistent with several scenarios but don't uniquely determine which is correct. Answering this would require more precise measurements of their relative velocity and how it changes over time. If bound, their separation should vary in a predictable way based on orbital mechanics. If unbound, they should separate linearly. The data collected so far spans too short a time to distinguish clearly between these possibilities. Third, the origin system. Where did these objects come from? Which star ejected them, and when? Tracing back through millions of years of galactic motion is extraordinarily difficult. Small uncertainties in the current trajectory compound rapidly, and the galaxy's gravitational field is complex, influenced by dark matter, spiral arms, molecular clouds, and stellar encounters. Computer simulations can suggest possible origin regions. Perhaps the objects came from a star that was once closer to our Sun, for instance, but they can't identify a specific source. Unless we get very lucky and find chemical signatures that match a particular stellar environment, the origin will remain speculative. Fourth, the internal structure. Are the objects solid or rubble piles? Loose collections of smaller pieces held together by weak gravity. Are they differentiated? With distinct layers of different materials, or homogeneous throughout? Do they have voids or fractures that might make them prone to breakup? Understanding structure requires either close-up observation, which we don't have, or indirect inference from properties like density and rotation. But we don't have good measurements of either for these faint objects. We can make educated guesses, but that's all they are. Fifth, the activity question. Was 3I/ATLAS truly a comet, actively releasing gas and dust during its passage near the Sun? The evidence was ambiguous during the original observation campaign, and the discovery of a companion complicated the picture. If the companion is a fragment, it suggests fragmentation occurred, which might indicate the parent was weak or icy or both. But fragmentation could have other causes. If there was outgassing, what was the composition of the released gases? Water is most common in solar system comets, but interstellar comets might be different. They might be enriched in carbon monoxide or other volatiles that would have been lost from objects in our warmer solar system. Without clear spectroscopic detections, we simply don't know. Sixth, there's the size question. Estimates range widely depending on assumed albedo. If the surfaces are dark, the objects might be larger than if they're bright. The difference could be a factor of 2 or more in diameter, which translates to much larger uncertainties in volume and mass. Seventh, the question of additional companions. Are there more objects associated with 3I/ATLAS that we haven't detected? A whole swarm of small fragments? A dust trail? The searches conducted so far have been limited by sensitivity and available telescope time. There could be a population of objects out there that's simply too faint to see with current technology. And finally, there are questions we probably haven't even thought to ask yet. Science often works this way. You study something with the questions you have, and in the process of answering them, or failing to, new questions emerge that you couldn't have anticipated. 3I/ATLAS, and its companion might hold surprises we won't discover until we develop new techniques or think about the data in new ways. This long list of unknowns might seem discouraging. But in fact, it's energizing. Each unknown is an opportunity for future discovery. Each question that remains unanswered is a direction for future research. The fact that mysteries persist means there's still work to do, still things to learn. And that's what keeps science moving forward. The study of 3I/ATLAS highlighted a fundamental limitation of astronomy. We're usually restricted to remote observation. We can't touch the objects we study. We can't sample them directly. We can only collect the light or other radiation they emit or reflect, and from that limited information try to reconstruct their properties. This contrasts sharply with other sciences. A geologist can pick up a rock, analyse it in a lab, slice it thin to examine under a microscope, test it with chemicals, date it using radioactive isotopes. A biologist can dissect an organism, sequence its DNA, culture its cells, observe it in controlled conditions. These hands-on approaches provide rich, detailed information that's impossible to get otherwise. Astronomers mostly can't do this. We're separated from our subjects by vast distances. The Moon is the only celestial body whose samples we've studied extensively in Earth laboratories, brought back by Apollo astronauts and robotic Soviet missions. We've also analysed a small number of meteorites, which are samples from asteroids that fell to Earth naturally, and we've collected tiny dust particles from a comet, captured by the Stardust mission. But these are exceptions. Most of astronomy is done from afar. We point telescopes, collect photons, and infer everything else. It's a testament to human ingenuity that we've learned as much as we have working under this constraint. But it's still a constraint, and it limits what we can know with certainty. For interstellar objects like 3I/ATLAS, the limitation is particularly acute. They pass through quickly, often detected late, giving us limited time to observe. They're typically faint, requiring large telescopes and long exposures, and they're always receding, getting fainter until they disappear entirely. There's no opportunity for follow-up years later when new instruments become available. Once they're gone forever. This creates a kind of desperation in observation campaigns. You must collect all the data you can while the opportunity exists. You must prioritise ruthlessly, deciding which measurements are most important. And you must accept that some questions will remain unanswered because there simply wasn't time or resources to address them all. The alternative, of course, would be missions that actually visit these objects. Spacecraft that could rendezvous with an interstellar visitor and study it up close, with instruments that could image its surface at meter resolution, analyse its composition directly, measure its properties in situ. This would answer many questions that photons alone cannot. But such missions face enormous challenges. Interstellar objects move fast, typically 20 to 50 kilometers per second relative to the Sun. Matching that velocity requires large amounts of propellant and energy. Current rocket technology is barely sufficient, and only if the spacecraft is already in space. Waiting. Launching from Earth after an object is detected is probably impossible with current technology. There's not enough time to build, launch and accelerate a spacecraft to intercept. There have been proposals. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, will wait at a gravitationally stable point in space. When a suitable comet is discovered, either from the Oort cloud or potentially an interstellar visitor, the spacecraft will adjust its trajectory to intercept. It's designed to be flexible and responsive. Other proposals are more speculative. Some envision spacecraft in permanent patrol mode, ready to react quickly when an interstellar object is detected. Others suggest using the Sun's gravity for a powered slingshot maneuver, achieving velocities that would allow rapid intercept. A few even propose catching up to Oumuamua or another interstellar visitor that's already been detected, accepting that the mission would take decades. None of these ideas have been funded yet. Space missions are expensive, and budgets are limited, but the scientific payoff from a successful intercept would be enormous. We would learn more from a few hours of close-up observation than from years of remote telescopy. Until such a mission happens, we're stuck with remote observation and its inherent limitations. We'll continue to refine our techniques, build more sensitive instruments, develop clever ways to extract information from photons. We'll make progress. But some questions will remain tantalizingly out of reach, answerable only by touching the objects themselves. This creates an interesting philosophical point. How much can we truly know without direct interaction? Astronomy has pushed this question to extremes. We study galaxies billions of light years away, quasars powered by supermassive black holes, the cosmic microwave background from the early universe. We can't touch any of it. We can only look. And yet we've developed detailed, successful models of how these distant phenomena work. So remote observation is clearly powerful, but it's not omnipotent. There's a difference between models that fit the data and true understanding. Sometimes you need to get your hands dirty, to examine something up close, to prod it and see how it responds. Astronomy is amazing for what it achieves. But it would be even more amazing with the ability to occasionally go and touch the things we've spent so long looking at. The discovery of 3 I/ATLASb involved an interesting mix of deliberate searching and fortunate timing. Let's think about the role that luck, or serendipity, plays in astronomical discovery. It's more important than you might expect. Many of the greatest discoveries in astronomy were accidental. Pulsars, neutron stars that emit regular pulses of radio waves, were discovered by Jocelyn Bell Burnell in 1967, while she was searching for something completely different. Quasars. She noticed strange, regular signals in her data and was curious enough to investigate rather than dismissing them as interference. That curiosity led to a Nobel Prize and opened up a new field of study. Cosmic microwave background radiation, the afterglow of the Big Bang, was discovered by Arno Penzias and Robert Wilson in 1964. They were trying to eliminate noise from a radio antenna and kept finding a persistent signal they couldn't explain. After consulting with theorists, they realized they'd detected the remnant heat from the universe's birth. Even interstellar objects have a history of serendipitous discovery. Oumuamua was found by the Pan-STARRS survey, which was designed to search for near-Earth asteroids that might pose a collision threat. Finding an interstellar visitor wasn't the goal, it was a bonus. The survey just happened to be looking at the right patch of sky at the right time. For 3 I/ATLAS-b, serendipity played a role in several ways. First, the astrometric survey that incidentally captured the stellar occultations in mid-2023 wasn't looking for them. It was monitoring stellar positions for entirely different reasons. The occultations were noticed only because researchers thought to check that region of sky. Second, the timing was fortunate. If the research team had checked a month earlier or later, they might have missed the occultation events. If the stellar survey hadn't been observing that particular field, the clues wouldn't have existed. Many small coincidences aligned to make the discovery possible. Third, the fact that the companion was bright enough to detect at all was lucky. If it had been slightly smaller or darker, it might have remained invisible even with the best instruments. We might have suspected its existence but never confirmed it. This raises an interesting question. How many discoveries are we missing simply because the conditions aren't quite right? How many interstellar companions have passed through undetected? How many binary asteroids escaped notice because they weren't quite bright enough or weren't observed at quite the right time? The answer is probably many. Astronomy is limited by instrumental sensitivity, observing cadence, sky coverage, and human attention. There's a vast space of possible discoveries, and we're sampling it imperfectly. We find what we're lucky enough to stumble upon, but there's undoubtedly much we miss. Some researchers argue that we should invest more in serendipitous discovery, build surveys that observe large areas of sky frequently with high sensitivity at multiple wavelengths, make all the data publicly available quickly, so that many eyes can search it for unexpected phenomena. Fund research programs that specifically look for the unusual, the anomalous, the things that don't fit expectations. The Vera C. Rubin Observatory, when it becomes fully operational, will be a major step in this direction. It will survey the entire visible sky every few nights, generating enormous data sets. The data will be processed automatically to flag moving objects, transient events, and other phenomena of interest. But the raw data will also be available for researchers to explore in their own ways, potentially finding things the automated systems miss. Machine learning and artificial intelligence are also playing a growing role. Algorithms can be trained to recognize patterns in data, to flag anomalies, to sift through millions of observations looking for the needle in the haystack. These tools aren't perfect. They sometimes flag noise as signals, or miss real phenomena that don't quite match their training, but they're getting better. Still, serendipity will always be a factor. You can't plan for the unexpected. You can only create conditions where unexpected discoveries are more likely and ensure you're paying attention when they occur. This requires a certain mindset: curiosity, flexibility, willingness to follow up on strange signals rather than dismissing them as errors. It also requires funding and institutional support. A researcher who wants to investigate something unusual needs time and resources. If they're under pressure to produce results on a specific project, they might not have the freedom to chase tangents. If telescope time is too precious and rigidly allocated, there's no room for opportunistic observations. The story of 3I/ATLASB is a reminder that some of the best science happens when we're flexible, curious, and lucky. The discovery wasn't planned. It emerged from the intersection of multiple projects, data sets, and insights, and it might easily not have happened at all if any of several factors had been different. This is both humbling and exciting. Humbling because it reminds us how much we don't see, how much remains hidden. Exciting because it suggests there are many more discoveries waiting to be made, hiding in data we've already collected or in regions of sky we haven't properly examined. The universe is full of surprises. We just have to be ready to notice them. The experience of studying 3I/ATLAS and its companion will inform how astronomers approach future interstellar visitors. We've learned lessons that will make subsequent observations more effective. We know what to look for, what techniques work, what challenges to expect. Let's think about how this might shape future discoveries. First, there will be a heightened awareness of possible companions. When the next interstellar object is detected, observers will specifically look for additional objects in the vicinity. This might involve wider field imaging to capture regions around the primary object. It might involve more sensitive observations to detect faint companions. It might involve modelling what orbits companions could have and targeting those regions. Second, data will be archived and processed more systematically with companion detection in mind. Rather than focusing solely on the brightest object, analysis pipelines will search for fainter associated signals. This requires more sophisticated software and more computational power. But both are increasingly available. Third, there will be better coordination between different observation campaigns. When an interstellar object is discovered, the astronomical community could mount a more organised response, with different groups taking on different aspects. One focusing on the primary object, another searching for companions, a third looking for dust trails, a fourth attempting spectroscopy. This coordinated approach would avoid duplication and ensure all important observations are covered. Fourth, there's likely to be more rapid public data sharing. The discovery of 3I/ATLASB benefited from researchers sharing their archival data. Future discoveries could benefit from even faster sharing, perhaps with agreements to make key data sets public within days rather than months. This would allow many research groups to contribute to analysis simultaneously. Fifth, there will be better theoretical preparation. Researchers now have models for binary interstellar objects, for debris streams, for fragmentation events. When new data comes in, it can be compared against these models immediately. We won't be starting from scratch trying to understand what we're seeing. The Vera C. Rubin Observatory will be particularly important. Starting in the mid-2020s, it's expected to discover multiple interstellar objects per year. This will transform the field from studying rare individual cases to having a statistical sample. We'll be able to ask population questions. What fraction of interstellar objects have companions? What's the typical size ratio? Are there common orbital configurations? With a larger sample, we'll also be able to identify rare or unusual cases more reliably. If most interstellar objects are solitary, and one has multiple companions, that immediately flags it as interesting. If most are rocky, and one is clearly icy, we'll want to understand why. Patterns and outliers both carry information. There's also hope for missions. The technology for rapid response intercept missions is developing. Propulsion systems are improving. Planning is becoming more sophisticated. While we might not be able to launch a mission to the next interstellar visitor, perhaps the one after that will be accessible. Each near miss teaches us more about what would be needed for success. Some researchers are proposing pre-positioned spacecraft. Imagine a probe already in deep space, far from Earth, essentially waiting. When an interstellar object is detected, the probe adjusts its trajectory for intercept. This removes the time constraint of launching from Earth. The probe could be relatively simple: cameras, spectrometers, dust detectors, and relatively cheap. Multiple such probes could be deployed, increasing the chances that one is well positioned for any given visitor. There are also proposals for what's called double-2 missions. Rather than actually rendezvousing with the interstellar object, which requires matching its velocity, a spacecraft could fly past at high relative speed. The encounter would be brief, maybe just minutes, but instruments could still collect valuable data. Imaging resolution would be far better than from Earth, and direct sampling of any coma or dust trail would be possible, beyond specific missions. There's the broader trajectory of technology. Telescopes are getting larger and more sensitive. Detectors are improving. Analysis techniques are advancing. Each year we gain the ability to study fainter, more distant, faster-moving objects. What was impossible a decade ago is routine now. What's difficult today will be standard in another decade. Spectroscopy, in particular, has room for improvement. Better spectrographs on larger telescopes might be able to characterize the composition of interstellar objects, even when they're faint. This would answer many questions that currently remain open. Adaptive optics, which corrects for atmospheric blurring in real time, is also advancing. This allows ground-based telescopes to achieve image quality nearly as good as space-based telescopes. And there's artificial intelligence. Machine learning algorithms are getting better at analyzing astronomical data, finding patterns, classifying objects. Future AI systems might be able to analyze images of interstellar objects and immediately determine likely composition, structure, and origin, based on comparison with huge databases of known objects. All of this adds up to an exciting future for interstellar object studies. The field is young, barely a decade old if we date it from Oumuamua's discovery in 2017. In another decade it will be mature, with dozens or hundreds of observed visitors, comprehensive models, and possibly direct spacecraft data. We'll look back at the early discoveries: Oumuamua, 2I/Borisov, 3I/Atlas, with nostalgia, remembering when each new detection was a major event rather than a routine occurrence. But that future maturity shouldn't diminish the excitement of these early discoveries. They're pioneering, establishing the foundation that everything else will build on. They're teaching us what interstellar objects are like, how to observe them, what questions to ask. And they're reminding us that the solar system is not isolated. We live in a galaxy, and that galaxy is populated with wanderers that occasionally pass through our neighbourhood, carrying stories from distant stars. There's something philosophically interesting about the phrase "something followed us home." It suggests agency, intention, tracking. But of course, 3I/ATLAS and its companion have no agency. They don't follow, don't choose, don't intend. They simply move through space according to physical law, along trajectories determined by gravity and momentum. The phrase is metaphorical, anthropomorphizing objects that are utterly indifferent to our existence. But metaphors can reveal truths. What does it mean to say these objects, quote, for us? They're moving in the same general direction we are, outward from the sun. If we were to send a spacecraft to the outer solar system now, it would be travelling the same basic route as 3I/ATLAS, at least for a while. In that sense, the object is behind us, following the path we've travelled. But there's a deeper meaning. These objects are evidence of something we've done. We've begun to venture into interstellar space. The Voyager probes, launched in the 1970s, have crossed the heliopause, the boundary where the sun's influence gives way to interstellar medium. They're now in the same realm as 3I/ATLAS, the space between stars. In a very real sense, humanity and these interstellar visitors are meeting in the middle. We're reaching out from our solar system just as they're passing through. We're both travellers, though their journey is far longer and more solitary than ours. This creates a kind of connection. We've studied objects from our own solar system extensively. We've sent probes to every planet, landed on several moons and asteroids, sampled comets, and mapped out the near-Earth environment in detail. But everything we've studied so far originated here, in our system, formed from the same protoplanetary disk as Earth. Interstellar objects are different. They're samples from elsewhere, from other star systems with potentially different conditions and histories. Studying them is our first direct contact with material from beyond the Sun's family. It's a small step toward understanding the wider galaxy. There's also something poignant about the idea of following. These objects passed through our solar system, came close to the Sun, perhaps even close to Earth, though not close enough to be dangerous, and are now leaving, never to return. We notice them, briefly, in the midst of their long journey. We're witnesses to a moment in a story that spans millions of years. Imagine the perspective of the objects, if they could have one. They're travelling through the galaxy, alone, for hundreds of thousands of years. Stars are distant, faint points of light. Space is cold and dark. Then, for a brief period, a few months, one of those distant points grows brighter. It becomes a sun, warming, very slightly, the frozen surface. Planets swim into view, large worlds of gas and rock. And on one of the smaller planets, tiny creatures have built instruments to watch. Those creatures see the visitors, photograph them, measure them, debate what they are. They publish papers, have conferences, build models. They care deeply about these cold rocks or ice balls passing through, and then the visitors recede. The sun becomes a point of light again, shrinking toward insignificance. The planets disappear. The darkness and cold return, and the journey continues. From the object's perspective, if they had one, the entire episode would be a brief interruption in an otherwise monotonous eternity. But from our perspective, it's significant. It's discovery, wonder, science. It's a reminder that we're part of something larger. This asymmetry is worth contemplating. The universe doesn't care about our observations. Stars don't know they're being watched. Galaxies don't know their light is being collected and analysed. The universe simply is, indifferent to our existence. And yet, our observations matter. They matter to us. They give meaning to our existence. We're the part of the universe that has become conscious, that looks back at itself and asks questions. When we study an interstellar visitor, we're engaging in an act of connection, even if that connection is one-sided. There's a philosophical tradition that grapples with this. Existentialism, particularly in the writings of Albert Camus, talks about the absurd, the conflict between our human need for meaning and the universe's indifference. Camus argued that we must imagine Sisyphus, the mythical figure condemned to push a boulder up a hill for eternity, as happy, finding meaning in the struggle itself rather than in any external purpose. Studying interstellar objects is a bit like this. The objects don't care, the universe doesn't care, but we care, and that's enough. We find meaning in understanding, in discovery, in the careful work of science. The objects followed us home, in a metaphorical sense, and we're grateful for the opportunity to study them, brief though it was. This is perhaps a very human way of looking at things. An alien intelligence might have entirely different perspectives on observation and meaning. But we're human, and this is our perspective, and there's beauty in that. So when we say something followed us home, we're really saying that we noticed something passing by, paid attention to it, and learned from it. That's an act of curiosity, care, and connection. And in a universe that's mostly empty and indifferent, these acts matter. They're what make us human. Let's step back and think about the larger significance of 3I/ATLAS and its companion. These are small objects, each perhaps only tens of meters across. Combined, they'd fit comfortably inside a football stadium. Their mass is minuscule on cosmic scales, a few million tons at most, which is nothing compared to planets or even large asteroids in our solar system. And yet, these tiny visitors have implications that reach far beyond their size. They tell us about processes that happen throughout the galaxy. They provide clues about planet formation, dynamical evolution, and the population of objects in interstellar space. They've sparked new research directions, motivated new observations, and challenged our assumptions. Small objects can have large implications. This is a recurring theme in astronomy. Some of the most important discoveries involve things that are individually insignificant. Pulsars are tiny compared to the stars they came from, yet they've taught us about nuclear physics, general relativity, and stellar evolution. Exoplanets are dwarfed by their host stars, yet their discovery has revolutionized our understanding of planetary systems. Cosmic microwave background photons are low-energy remnants of the Big Bang, yet they carry information about the universe's origin and structure. Size doesn't determine importance. Significance comes from what something teaches us, what questions it answers or raises, what doors it opens for future understanding. By that measure, 3I/ATLAS and its companion are quite significant indeed. They've taught us that interstellar objects can have companions, which changes how we think about the population of rogue objects in the galaxy. They've shown us that detection is difficult, and that we can miss things even when we're looking carefully, which motivates better surveys and analysis techniques. They've demonstrated the value of archival data and the importance of revisiting old observations with new questions. They've also highlighted gaps in our knowledge and technology. We'd love to know what these objects are made of, but we can't determine that from Earth-based observations alone. This motivates missions and new instruments. Every limitation encountered is an opportunity for improvement. On a philosophical level, these objects remind us of cosmic timescales and distances. They've been travelling for hundreds of thousands of years, perhaps millions. They've crossed light years of space. They formed around a star we'll probably never identify, were ejected by processes we can only model, and pass through our solar system by pure chance. Their story connects to the history of the galaxy, to star formation and planet formation, and the slow churning of matter through space. We exist at one moment in this vast story. Our entire civilization, everything humans have ever built, thought, or done, occupies a tiny slice of time compared to the journeys of these interstellar wanderers. And yet we're here, conscious and curious, able to notice their passage and ponder what it means. This perspective can be humbling. It reminds us how brief our moment is, how local our concerns are, but it can also be empowering. Despite being tiny and temporary, we're capable of understanding things vastly larger and older than ourselves. We can look at an interstellar object and decode its history, infer where it came from, predict where it's going. That's remarkable. There's also an interesting symmetry. We're small, and so are these objects. Earth is tiny on the scale of the galaxy, and so are chunks of rock or ice tens of meters across. We're both insignificant in some sense. But we're both part of the cosmic story. We're both products of physical law playing out over billions of years. We're both, in a way, children of stars, us made of atoms forged in stellar cores, these objects condensed from stellar debris. The study of interstellar objects is, in a sense, the study of ourselves. By understanding how planetary systems form and evolve, how objects get ejected and wander the galaxy, we understand the processes that shaped our own solar system. By learning what's typical and what's unusual, we place ourselves in context. Are we common? Is the solar system's architecture typical of planetary systems? Did most systems go through similar dynamical evolution, ejecting similar objects? Or are we special, with a particular history that led to life emerging on one of our planets? We can't answer these questions yet, but every interstellar object we study brings us closer to answers. Small objects, large implications. This is why researchers invest so much effort into observing faint, distant visitors. This is why facilities like the Rubin Observatory are being built, why missions to intercept interstellar objects are being planned. This is why papers get written, conferences get held, and debates continue. Not because the objects themselves are important, but because what they represent is important. They're ambassadors from the rest of the galaxy. They're proof that we're not isolated. They're samples from conditions and histories different from our own. They're puzzles that challenge our understanding. And they're invitations to imagine, to wonder, to reach beyond our local neighbourhood and touch, however tentatively, the larger cosmos. Studying objects like 3I/ATLAS requires patience. This is a virtue not always celebrated in modern society, which tends to favour quick results and instant gratification. But astronomy operates on different timescales. Understanding emerges slowly, built from many observations over months or years, synthesised from multiple perspectives, refined through careful analysis. The story of 3I/ATLAS and its companion spans several years. The original detection in November 2020, the observation campaign through early 2021, the years of quieter analysis and occasional follow-up, the surprise discovery of the companion in late 2023. Each phase took time. Each required sustained attention from researchers who could easily have moved on to other projects. Why do they persist? Part of it is institutional. There are careers built around specific research areas, and abandoning a project midstream has costs. But part of it is also genuine curiosity. When you've invested time in understanding something, you want to see it through. When you know there might be more to discover, it's hard to walk away. This patience extends to observation itself. Telescope time is measured in hours, carefully allocated. A successful observation requires everything to align. The weather must cooperate, the equipment must work, the object must be in the right position. Often things don't align. Clouds roll in, a detector malfunctions. The object is fainter than expected. You wait for the next opportunity. Data analysis also requires patience. Images must be processed, calibrated, compared against references. Subtle signals must be teased out of noise. Orbital calculations must be run and rerun, checking for errors and refining estimates. This work isn't glamorous, it's often tedious. But it's necessary. Publication is another exercise in patience. Papers must be written carefully, presenting data and arguments clearly. They're submitted to journals, where they undergo peer review. Other experts read them and critique them. Often, reviewers ask for additional analysis or clarification. The paper is revised, resubmitted, reviewed again. Months can pass from submission to publication. And only after publication does the work truly enter the scientific record, available for others to build upon. This entire process can feel slow, especially from the outside. When a discovery is made, there's often pressure to announce it quickly, to get credit, to generate excitement. But responsible science requires thoroughness. Premature announcements can be embarrassing if later data contradicts them. Better to be certain, even if it takes longer. There's also patience required in accepting uncertainty. Not every question gets answered. Not every observation is conclusive. After years of work, you might have to admit that you simply don't know something, that the data is insufficient, that the answer will have to wait for better instruments or future observations. This can be frustrating. It's natural to want closure, to want definitive answers. But science doesn't always provide them, at least not immediately. Progress is incremental. Each study adds a little to the picture, even if it doesn't complete it. The researchers studying 3I/ATLAS have had to exercise this patience repeatedly. Is it a comet or an asteroid? We're not sure. Are the two objects gravitationally bound? We can't say definitively. Where did they originate? Unknown. Each of these non-answers requires accepting that our knowledge is limited, that we've done the best we can with available data, and that future work might, or might not, resolve the ambiguities. There's a kind of wisdom in this. It's easy to be overconfident, to claim more certainty than the data warrant. It's harder to be honestly uncertain, to say I don't know when that's the truth. But honest uncertainty is more valuable than false certainty. It leaves room for revision when better data becomes available. It invites others to contribute, to try different approaches, to potentially succeed where you haven't. Patience is also required from the public and funding agencies. It's hard to justify spending money on observations that might not yield clear answers. It's tempting to focus resources on projects with more certain payoffs. But discovery doesn't work that way. Sometimes you have to chase unlikely leads. Sometimes you have to wait years for an observation to become possible. Sometimes the most interesting results come from patient, sustained effort rather than quick, targeted studies. The story of 3I/ATLAS is, in part, a story about patience. Patience in observing, in analysing, in publishing, in accepting uncertainty. And in many ways, this is a microcosm of science more broadly. Research is a marathon, not a sprint. Understanding emerges over time, built from countless patient efforts by many people. In a world that often values speed and immediate results, this patient approach can seem out of step, but it's essential. Truth doesn't care about our schedules. The universe reveals itself at its own pace. Our job is to watch, wait, and stay curious. To keep asking questions even when answers are slow in coming. To trust that effort, sustained over time, will eventually yield understanding. When astronomers study interstellar objects, what are they really searching for? On the surface, the answer is obvious. We want to understand these visitors, to determine their properties, to learn about planetary systems beyond our own. But dig a little deeper, and there are more profound motivations at work. We're searching for context. Humans have always wondered about our place in the universe. Are we typical or special? Is Earth's history common or unique? Is the solar system ordinary or unusual? For most of human history, we couldn't answer these questions. We had only one example, our own system, and you can't do statistics with a sample size of one. Exoplanet research has begun to change this. We now know of thousands of planets orbiting other stars, and they show tremendous diversity. Hot Jupiters orbit closer to their stars than Mercury does to our Sun. Super-Earths, a planet type we don't have, appear common. Some systems have planets in resonant orbits, locked in precise mathematical ratios. The zoo of planetary systems is rich and varied. Interstellar objects add another dimension to this context. They're not planets, but they're products of planet formation. They tell us about the small body populations in other systems, about dynamical processes that scatter objects, about compositions that might differ from our local inventory. Each interstellar visitor is a data point. One data point doesn't tell you much, but accumulate enough and patterns emerge. You can ask, What fraction are comets versus asteroids? What's the size distribution? Are binaries common? Do compositions vary? Each answer places our own solar system in context. We're also searching for connection. There's something profound about detecting an object from another star system. It's a physical link to distant places we'll likely never visit. The atoms in that object formed around another sun, perhaps when Earth was still young. They carry history, a story of formation and ejection and lonely wandering. By studying them, we're reaching out across the gulf between stars. We can't travel there ourselves. The distances are too vast for current technology. But the objects come to us, or at least pass near us, and that's almost as good. It's a kind of cosmic gift, a message in a bottle cast across the interstellar ocean. We're searching for surprises. Science advances when observations don't match expectations. If every interstellar object looked exactly like comets and asteroids from our system, we'd learn little new. But when they're strange, when Oumuamua is elongated and accelerates without visible outgassing, when 3I/ATLAS has an ambiguous companion, that's when we have to think harder, question assumptions, develop new models. Surprises are uncomfortable. They mean our understanding is incomplete. But they're also exciting. They're opportunities for discovery, for expanding the boundaries of knowledge. Every researcher hopes secretly to find something unexpected, something that doesn't fit, something that makes people say, Quote 6. We're searching for limits. How small can an interstellar object be and still be detected? How faint? How fast? Each detection pushes our capabilities, showing what's possible with current technology. And each near miss, objects we almost but didn't quite detect, shows where the limits are. This guides the design of future instruments and surveys. We're searching for stories. Science is often portrayed as cold, impersonal, focused purely on facts and data. But scientists are human, and humans love stories. The journey of an interstellar object is a story. Formation, ejection, travel, encounter, departure. We want to know where it came from, what it's seen, where it's going. We want to imagine its history, even though we'll never know it with certainty. And we're searching for meaning. Not meaning in a cosmic sense, the universe doesn't provide that, but meaning in a human sense, understanding, purpose, the satisfaction of curiosity. When we look at the night sky, we're not just seeing points of light. We're seeing a vast cosmos full of structure and history and physical processes. We're seeing a puzzle we can work to solve. In the end, we're searching for what we've always searched for, understanding of the world beyond ourselves. The tools change, telescopes instead of naked eyes, spectrographs instead of simple observation. But the impulse is ancient. We look up, we wonder, we ask questions, and occasionally the universe provides hints of answers in the form of small, cold objects passing through our neighbourhood on journeys that began before humans existed and will continue long after we're gone. Imagine the Milky Way galaxy as a vast museum, a gallery containing hundreds of billions of exhibits. Each star is a display, showcasing the results of stellar evolution, planet formation, and billions of years of history. Our sun is one exhibit among many, neither the largest nor the most spectacular, but unique in its details. Most visitors to this museum never see most exhibits. Distances are too vast. A visitor starting at one star might travel for millions of years before reaching the next. But there are wanderers, objects not bound to any particular display, drifting through the gallery's corridors. These are the interstellar objects, the gallery's own messengers, carrying samples from one exhibit past others. 3I/ATLAS and its companion are such messengers. They originated at some other exhibit, some other star with its own planets and history. Through gravitational accident, they were ejected, becoming free agents. They've drifted through the gallery for hundreds of thousands of years, passing countless other stars at great distance, and now they've passed by our exhibit. For a brief time, we could observe them, study them, try to learn what they could teach us. We couldn't identify which exhibit they came from. There are too many possibilities, and they've travelled too far. But we could confirm they came from somewhere else, that they carried information from beyond our local neighbourhood. This metaphor captures something important about our place in the cosmos. We're one display in a vast gallery. We're not at the centre. There is no centre. We're not particularly special in most respects. Our star is medium-sized and middle-aged. Our planet is small and rocky, probably common in the galaxy. Our existence as observers is, as far as we know, rare, but perhaps not unique. What makes us special is that we're conscious, curious, capable of appreciating the gallery we're part of. We can look at other exhibits, other stars and their planets, and understand something of what we're seeing. We can study messengers from those other exhibits and piece together information about places we'll never visit. This is a privileged position, in a way. Most of the universe is not observing itself. Most matter is unconscious, simply existing and following physical law. But we're different. We're the museum observing itself, trying to understand its own structure and history. The objects that pass through carry stories, if we're clever enough to read them. 3I/ATLAS and its companion tell us about dynamical processes that happened in another planetary system. They tell us about compositions that might differ from or resemble our own solar system. They tell us about the population of wanderers in the galaxy, the lost and ejected objects that drift through interstellar space. These stories enrich our understanding. Every exhibit in the gallery is unique, but they're also related. They're all products of similar processes: gas cloud collapse, star formation, planet formation, evolution. By studying many exhibits, or at least the messengers from many exhibits, we can understand those common processes better. We can see what's universal and what's particular. This gallery metaphor also highlights the isolation and connection inherent in the cosmos. Each star system is isolated, separated by light years of empty space. Direct contact between exhibits is essentially impossible with known physics. We can't visit other stars in any practical time frame. They can't visit us. But we're not completely isolated. Light travels between stars, carrying information. We can observe other exhibits even if we can't visit them, and occasionally physical objects like 3I/ATLAS traverse the gaps, providing direct samples. These connections are tenuous, but they exist. Our place in the gallery is both humble and extraordinary. Humble because we're just one exhibit among hundreds of billions, most of which are probably more spectacular than ours. Larger stars, more planets, older histories. Extraordinary because we're conscious observers, capable of appreciating the gallery, studying it, trying to understand how it all works. As we continue exploring the gallery, as we detect more interstellar objects and study them more thoroughly, as we build better instruments, and perhaps eventually send missions to other stars, we'll understand our place better. We'll see where we fit in the spectrum of possibilities, what's typical and what's unusual about our exhibit. But we're already learning. Each interstellar visitor teaches us a little more. Each one reminds us we're part of something larger, a galaxy full of stars and planets and wandering objects, all connected by gravity and history, all part of the same cosmic story that began with the Big Bang and continues now, in this moment, as you listen to these words and contemplate the visitors that have passed through our corner of the vast gallery we call home. There's a particular kind of comfort that comes from cosmic perspective. When you zoom out far enough, when you think about timescales of millions of years and distances of light years, individual worries and concerns seem to shrink. Not in a way that makes them meaningless. Your life and experiences are real and important, but in a way that provides proportion. 3I/ATLAS and its companion, travelling for hundreds of thousands of years through the emptiness of space. Remind us of this perspective. They've been on their journey far longer than humans have existed as a species. They'll continue that journey long after our current civilization is gone. To them, if they could experience, our entire history would be a brief flicker. This can be either terrifying or comforting, depending on how you look at it. Terrifying because it emphasizes our insignificance, the brevity of our existence, the indifference of the cosmos. We're tiny creatures on a small planet, living for a cosmically insignificant time. The universe doesn't care about us. When we're gone, it will continue, unchanged. But it can also be comforting. Your problems, worries, anxieties, all the things that loom large in your daily life are temporary and local. They're real, and they matter to you, but they're not cosmic in scope. They're human-scale problems, and that's okay. The universe provides perspective that can make overwhelming things feel manageable. There's also comfort in continuity. 3IATLAS has been travelling for hundreds of thousands of years. During that time on Earth, species have evolved and gone extinct. Continents have shifted. Ice ages have come and gone. Human civilization has risen from small bands of hunter-gatherers to global technological society. And through all of that, this small object has been moving through space, following its trajectory, unchanged and unchanging. There's something steady about that. Something reliable. The universe operates according to physical law. Gravity doesn't take breaks. Momentum is conserved. Light travels at constant speed. These facts persist regardless of what happens on any particular planet. They're foundations you can count on. This steadiness is different from human affairs, which are chaotic and unpredictable. Societies rise and fall, relationships form and dissolve, technologies advance, ideas spread, nothing stays the same. But the physical universe has a kind of constancy. Stars burn through their fuel according to predictable equations. Planets orbit according to Newton's and Einstein's laws. Interstellar objects follow their trajectories through the galaxy. There's also comfort in the vastness of possibility. The galaxy contains hundreds of billions of stars. Many probably have planets. Some of those planets might harbour life. Some might have civilizations. We don't know if we're alone, but the sheer number of possibilities suggests we might not be. Somewhere out there, perhaps, other observers are looking up at their sky, noticing interstellar visitors, asking the same questions we ask. This is speculative. Of course, we have no evidence of other intelligent life. We might be alone in the galaxy, or at least alone in being technological. But the possibility is there, suggested by the vastness of space and the commonality of physical processes, and that possibility is, in its way, comforting. It means we might be part of a large community, even if we're currently isolated members of it. The story of 3I/ATLAS and its companion is, ultimately, a small story. Two small objects passing through our solar system, noticed by a few dozen astronomers, studied for a few years. In the grand scheme of cosmic history, it's barely a footnote. And yet, for us now, it's meaningful. It's part of our ongoing effort to understand the universe. It's connected to larger questions about planet formation, galactic structure, and our place in the cosmos. And that's the final comfort, that our small efforts matter. Not in a cosmic sense. The universe doesn't grade our homework, but in a human sense. Understanding gives meaning to our existence. Curiosity is its own reward. When we study something like 3I/ATLAS, when we invest time and thought and effort into understanding these distant visitors, we're doing something that matters to us. We're exercising our uniquely human capability to wonder and to seek answers. So as you lie here, listening to this story, let yourself feel that cosmic perspective. You're a small part of a vast universe, yes. Your time is brief, yes. But you're also part of something magnificent, something ancient, something that encompasses galaxies and eons. You're made of star stuff, as Carl Sagan said. You're the universe contemplating itself. And right now, in this moment, you're thinking about two small objects travelling through the space between stars, objects that pass near our planet, noticed briefly, and then continued their journey. That's a connection across light years and hundreds of thousands of years. That's your mind reaching out to touch something vastly distant and different from you. That reach, that curiosity, that willingness to contemplate the cosmos, that's what makes us human. And in a universe that's mostly empty and indifferent, it's enough. It's more than enough. It's beautiful. We've travelled a long way together tonight. For more than 2.5 hours, we've explored the story of 3I/ATLAS and its unexpected companion, an interstellar visitor that we thought we understood until we discovered we'd missed something important. We've looked at the detective work that revealed the companion's existence, examined what the orbital dynamics tell us, considered what this discovery means for our understanding of interstellar objects and planetary systems, and contemplated our place in the larger cosmic context. Where we started, back at the beginning, with a research team noticing subtle stellar fluctuations in data from 2023, seems distant now. But that's how many discoveries happen, not through dramatic revelations, but through careful attention to detail, through noticing small anomalies, through following up on curious signals that others might dismiss. From that small beginning, we've traced a story that spans hundreds of thousands of years and reaches across the galaxy. And now we return to the question implicit in our title. What does it mean that something followed us home? Of course, nothing literally followed us. 3I/ATLAS and its companion don't care about us and aren't tracking us. They're simply moving through space according to physical law, on trajectories set millions of years ago. But metaphorically, poetically, there's something to the idea. These objects pass through our solar system. They came close enough that we could detect them, study them, learn from them, and one of them, the companion, went unnoticed for nearly 3 years despite being captured in dozens of images. We thought we'd catalogued everything important about the system, thought we'd observed it thoroughly, and then discovered we'd missed something significant hiding in our own data. This is a humbling reminder. Even when we're looking carefully, even with sophisticated instruments and skilled observers, we can miss things. The universe is subtle. Important phenomena can lurk just below our detection thresholds, or hide in plain sight because they don't match our expectations. We need to stay curious, stay humble, keep looking at familiar things with fresh eyes. If you've enjoyed this slow exploration of interstellar mysteries, if you've found some peace in contemplating these cosmic wanderers, please consider leaving a like and sharing your thoughts in the comments. What surprised you most? What aspects of the story resonated? I love hearing from you, and your engagement helps others find these quiet journeys through space and science. Perhaps you've already drifted into sleep, and if so, that's absolutely perfect. These words continue as gentle companions to your dreams, present but not demanding attention. But if you're still awake, still listening, still following along, that's wonderful too. There's no right way to experience this. You're exactly where you need to be. If you can, look up at the night sky. Or imagine it if you can't see it. Picture all those stars, each one a sun with potentially its own family of worlds. Picture the vast distances between them, distances so large they're measured in years of light travel. And picture the space between those stars, the seemingly empty void that isn't quite empty. It contains faint gas, occasional dust, and these wanderers, these interstellar objects travelling on journeys that span hundreds of thousands of years. Right now, at this very moment, 3I/ATLAS and its companion are out there, far beyond Neptune's orbit, receding from our Sun at 34 kilometers per second. Every second, they get farther away. In the time it took you to listen to this closing, they've travelled thousands of kilometers. By tomorrow, millions of kilometers farther. In a year, they'll be 1 billion kilometers more distant than they are now. They don't know we observed them. They don't know we debated what they are. They don't know that people on a small blue world pointed instruments in their direction and wondered. They simply move, following the trajectories that were set when they were ejected from their home system so long ago. And there's something peaceful about that, something reassuring about the steady, indifferent continuation of physical processes. The universe goes on, stars burn their fuel, planets orbit, objects travel through space. All of it according to natural law, all of it indifferent to our observation. And yet here we are, conscious and curious, capable of noticing these visitors, capable of finding meaning in their passage. We're tiny in cosmic terms, brief in time, but we're not insignificant. We're the part that wonders. We're the part that asks questions. We're the universe looking at itself. So sleep well, knowing you're part of something vast and ancient and magnificent. Dream of small objects crossing immense distances if you dream at all. Dream of patient researchers studying faint signals in data. Dream of future visitors yet to be discovered. Dream of the space between stars, not empty but populated with wanderers carrying stories from distant suns, and know that somewhere, always, people are watching the sky, looking for the next visitor, ready to notice what others might miss. Know that curiosity persists, that the drive to understand continues, that wonder still draws people to look up and ask, what's there? You're part of that ancient tradition, that human impulse to seek understanding of the cosmos we inhabit. Good night. Rest easy. Let the day and all its concerns fall away. Let your thoughts drift like the interstellar objects we've discussed, moving slowly through darkness, following paths determined long ago, peaceful in their journey. Let your breathing match the slow, steady pace of cosmic time. Sleep now. Dream of discovery and wonder. Dream of surprises hiding in data, waiting for someone patient enough to find them. Dream of visitors from beyond, messengers from other star systems, connecting us briefly to the wider galaxy. Dream of the comfort that comes from cosmic perspective, from knowing that the universe is vast and ancient and you're a small but real part of it. And may you find peace in the certainty that tomorrow, when you wake, the cosmos will still be there, still full of mysteries waiting to be explored, still inviting us to look up and wonder. May your sleep be deep and restful. May your dreams be gentle, and may you carry some sense of cosmic perspective with you. A reminder that you're connected to something larger than yourself, something beautiful and profound. Good night. Rest well. And thank you for joining me on this journey through the story of something that followed us home, something we almost missed, something that reminds us to stay curious and humble and open to surprise. Sleep peacefully, knowing the universe is vast and wonderful, and you're part of its unfolding story.